This video will look at a few perspectives for solving error detection and correction problems. Again, this video emphasizes the benefits and the value of solving problems by playing. Now, the best way to learn anything is to play. In the real world, if you break the rules, maybe or lose or loss, there may be consequences, but in the mathematical world, you could always play. Of course, when you violate a rule, you always realize it, that the rule ensures. But the best way to come up with solutions and ideas is to play with numbers so that you can come. Now this, when we try to, I was basically think about it, we would like, if you have a certain message or any piece of information to be coded, the theoretical definition says that when that information is transmitted across a particular medium, both the length and the value of the information can change. I'm not assuming the change in the length and the value. I'm assuming that can be taken care of. So if n bits are transmitted at one end, exactly n bits only are received at the other end also. So I'll assume that. But having assumed that, we could of course generalize also to other cases as well. Some of the simple ideas that you can come up with are, for instance, what happens if you take, say, generate a 4-bit code, say, a nibble, and find out what happens if exactly out of those codes that you generate, exactly 1 bit changes or 2 bit changes. What happens to all the codes? And how to ensure that. The objective is, now if you're trying to talk about error detection and correction, clearly the length of the code, compressed code, will have to slightly increase so that a bit of redundancy is introduced so that it can check against the redundant values to correct it. Now, a simple practical approach was now the main objective of error detection and correction is, if you have a certain sequence of message which is coded, then and it is the coded part which is transmitted. Now whatever this value is, if there are some changes to this code, which has been coded with some redundancy in this and transmitted across, if there are changes to this, it still does not change the value this code represents of this. This means a single value of the message must be coded to several possible values of the code. Meaning the size of the code in this case is the exact opposite of compression. You might think that just because it is the opposite of compression, we cannot possibly have a condensed coding of this message also here and included in the message itself. Actually, that is not really true. There are certain, for instance, there are many ways of going about thinking about that. We all know that NC, for instance, NC n by 2 nearly equal to 2 power n minus 1, that is half. So if you code only using n by 2 bits, so you must receive only n by 2 a code of if more ones come up or like that. But the problem is in that case that totally restricts it. That means you cannot use strings which have only one in it or 2 ones in it. For lesser values of r, you cannot use that. Rather, you could try to use selectively within the different values of r. These are all different strategies you can think of, but one simple practical way is I will do this for a byte, which is 8. I initially started off as a square and I was trying to do that as a square, but you don't need to. So I will take 8 points here. And here also vertically 8 points. And then basically I have here a triangle of points. So I have here, and this will be 9. Eight. Okay. So here, since we would like 9 as a code, so I will take here 9. For an 8-bit value, there should be 9 points. Here also finally 1. Now actually a 0 or a 1 is represented as a arrow going. This is the point of origin. So if I have an 8-bit code here, if I represent 1 as up and 0 as left. Okay. So now I am interested only in the diagonal. So I will number this 0, 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 points. So I am interested only in these 9. So if I have an 8-bit code, say some value, if it's all 0, 1, 1, 1, 1, 1, 1 is up. So it is like this. This is, it comes to 0. If it is all 0, 0, 0, it comes to this value 8. Most likely all of them, for every possible that is 8-bit code, will land up with only 1 point in the diagonal. Maximum we might expect around to come up in 4. So if the code, that means the point 4, this means what? The value 4 and a lot of different codes, lot of different values of the message is actually represented by the code 4. Right, so here what will happen, you will find 256 possible paths here already. But then close to around 54 or 64 paths will come up to 4. Right, so how many ways are there to get to 1? You could go this way, this and this. 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 Since you can't go right, there's no going this way. You can go this and this and this and this and this and this, like this. So this way, so what we can do is, this actually results in data compression only, but it can also be used, if this is the value that it represents, then changes, I was thinking if this is constant, since there are many possible values which represent this particular code represents a set of possible values. So it can be used for compression as well as combination of both, as a form of coding which is both a combination of error detection and correction as well as data compression. Essentially it provides compression only, but it's a useful tool for error detection and correction as well. This is an alternate way of coding information which affords compression and is also simultaneously for error detection and correction. Other strategies can also be adopted. This is a simple idea. Now once we come to this part, if we code, so any path that goes to 4, any code, any message, 8-bit message which it goes to 4 will be coded as 4. So the difference between this is, and the combinatorial one is, the distribution may not be identical to that of the combinatorial one. And also here you will find different number of ones and zeros. If you say NCR as a value, then for a given value of R, all of this set represents all those strings which have exactly R value, R ones in it. But here, even though a subset of 256 goes to 4 only, not all of them will have the same value of R. They will have different values of R, which means if something happens to a message where its ones and zeros change, that means and it does not come up to 4. If this part, the compressed part, is 4, then you know where it could have possibly changed. Because change, which most likely the value of R will change. If you even assume a combinatorial approach, most likely the value of R will change here every time there is an error, and if there is an error during transmission, the value of R is more likely going to change. The ideal situation is when you try to handle the number of error detection. The ideal way to perform error detection and correction is not through the computer or physically. You could always do that, but ideally in a network, if a node is transmitting across to its neighbor, it should know how many errors on an average it encounters on a particular line. So based on that, it should apply a particular algorithm which could be dynamic, which could adjust to the number of errors it finds in the state of the line and code accordingly. So as the number of errors increases, the size of the code it transmits also should slightly, not much, so that the amount of errors can be corrected. So because as we just saw, it is not necessary that the size of the code should actually increase if you try to do. So trying to solve a problem for error detection and correction, you always end up coming up with compression as well. Or trying to solve a problem for compression, you can always introduce redundancy to solve error detection and correction. Right? So a practical approach of playing with is the easiest and the best way to learn a particular topic.